let's get started with this webinar on quantum computing with the IBM Quiz Kit. So IBM Quiz Kit is the quantum computation library, which I will be giving you a demo at the towards the end of this session. So we will go through some concepts, some basic concepts on quantum computation, and we will discuss one very important algorithm. Yeah, Vishwas,
Yes, sir.
some people are waiting in the like
I've
waiting.
admitted them. I'm
Yeah, yeah,
admitting
yeah.
them.
You,
I am.
you please keep on admitting them.
Yes, sir. Sure.
Okay, thank you so much. So let's proceed with this, and yeah, thank you so much everyone for joining this session, and I hope you find this useful and just get some encouragement and motivation to start studying quantum computing as well. So this is the brief overview of the webinar. So I will start with the discussion of why quantum computing is required in today's industry. What are the various applications of quantum computing? Then we will see a brief comparison about classical and quantum computing and what are the properties which makes quantum computing so interesting. We will discuss very briefly about the quantum advantage, logic gates, and then the algorithm which I was speaking about is the Grover's search algorithm. And yeah, we will see it in the demo as well. So yeah, let's get started. So why quantum computing? You might have seen this diagram before also, because I hope that many are from engineering background, and you know that the classical computing is having the limitation of the circuit count. So as the circuits are diminishing in size, the quantum effects are like taking place. The quantum computing, not quantum computing, but the quantum tunneling of electrons starts taking place whenever your transistor size reduces. So that creates a lot of problem during the fabrication of your integrated circuits, which our laptops are made up of, laptops, mobile, and all electronic devices. So that's a limitation. So because of that, we are reaching a point where we cannot decrease the number of transistors in our circuits. So Moore's law is breaking. Moore's law said that, yeah, we will be able to double the number of transistor by 18 months, but that's not happening, and we are reaching a saturation point where quantum effects such as quantum tunneling effects of electrons are starting to dominate. And if that dominates, you can't make proper or perfect classical circuits. We need perfect classical circuits for proper classical computation, and that cannot happen if there is quantum mechanical effects taking place. So that's one of the reason. And another reason is the prime factorization. So you know, this kind of phenomena is important. Those who are uh, from background on like a cyber security and cryptography, they classical cryptography, so they will know the importance of prime factorization. And we know that in classical computers there is a limit where you cannot factorize large prime numbers. On the other hand, quantum computer is going to give you that advantage over classical computing, where you can really prime factorize large numbers. So those are one of the like primary reasons why we are moving towards quantum computing. And also there are like I will be discussing some few applications now, which also convinces you to move towards this field. Of course, we cannot use quantum computing for playing games right now because they are in early stages, but who knows, might be in future when the quantum computers also become perfect like classical computers, then quantum games might also become popular. So that's the thing. Now, some of the applications in quantum computing, for example, in the financial services industry, you use sampling techniques such as Monte Carlo simulation and all those stuff, which require huge amounts of computational power. For example, risk management. in finances and portfolio optimization, where you analyze lot of financial portfolios and reduce the financial risks. So those kinds of stuff require quantum computation, because using classical computers, it's not feasible to get a reasonable result, and it might take a long time to analyze those portfolios. So one of the like this is also one of the like primary you can say application, which is of optimization. Next is weather forecasting. Many of you might already know that in weather there are lots of variables involved. You know, there is air pressure involved in weather. Okay, there is a particular climate which happens at a certain region for many years. So you have the data for that, and yeah, there are many variables. So when the number of variables increases, the number of dimensions also increase, and because of that classical computers reach a limitation, because they cannot handle that much number of features, that much number of variables. So, and because of that, quantum computing, we need to focus on quantum computing because it gives you that inherent parallel power. It's an inherent parallel processor, quantum computing, quantum computer, that gives you that power to do inherent parallel processing of all the variables. And yeah, I have already mentioned about cryptography and cyber security, and it has been uh, said that if the quantum computers come into picture, then they can break all the classical encryption algorithms. But I can say you that there has been a recent development. I do not remember the name, but I think just a few days ago I read an article where, using the concepts of abstract algebra like homomorphism, researchers have developed an encryption technique which even quantum computers cannot break. So, if I remember correctly, that technique's name was homomorphic encryption, I think. So yeah, you can search about that. But yeah, it's a very recent article, and it was really interesting. Like I found it very really interesting because till now I heard that quantum computers, if they become perfect in future, they can break all the classical encryption methods, but with the introduction of homomorphic encryption, they now can't do that. So yeah, so when you have the cons, people try to search for pros as well. And another application of quantum computing is in chemistry and drug development. For example, there are some recent papers which I saw where people have used quantum machine learning, especially like quantum transfer learning, to detect COVID-19 cases. So they had a database of uh, large database of lungs images of COVID patients, and they have analyzed it using the technique of quantum transfer learning, which is definitely, it's a significant step towards this. And you will find there are many papers where people are simulating and modeling molecules which are used in drug development and material science, because you know the polymer molecules or the biological molecules, they have long chain reactions, and you need huge parallel power to process those, to model those molecules. So that's one of the key areas where quantum computing is helping. And of course, artificial intelligence and machine learning, we can't deny that we have lots of amount of classical data with us, lots of classical data, and now our goal has become to process all those classical data using quantum computers. So that's the field of quantum computing and machine learning, which people are really fascinated about, quantum machine learning. And yeah, tomorrow I am also going to give an expert talk on quantum machine learning. It's like on IEEE Signal Processing Society has invited me to give a talk on this fascinating technology. And yeah, so if you want to join, you can join definitely there also. So I will be discussing mostly about quantum machine learning stuff, how quantum computing is being applied in machine learning and what's the power. But one thing I want to mention here is that quantum computers are not perfect, and still there are lots of research going on in the quantum hardware because the quantum hardware itself is not perfect. The quantum logic, the quantum bits which we will be going through, they are not perfect. So once they get perfect, then only slowly quantum algorithms start making more sense and they can be useful. So yeah, so hardware is now the limitation, but yeah, we are slowly overcoming it, and we have NISQ devices, noisy intermediate scale quantum devices, for which researchers are trying to come up with applications where NISQ devices can suffice. So that's the point. And here we go. So this is the classical computing versus quantum computing difference. And you can see that classical computing, as you know, it's based on classical mechanics. You use classical bits 0 and 1, CMOS circuits, complementary metal oxide semiconductor circuits are used to manufacture classical computing devices such as your laptops, mobile, and every other electronic gadgets you have. And it uses central processing unit CPUs, which process the information, and this is an important point, in a sequential manner. And in quantum computing, on the other hand, in quantum computation, you use the principles of quantum mechanics to achieve quantum computation. You use something known as quantum bits called qubits, where the bits can be in superposition, and we will discuss this very soon. And the hardware varies, such as the yeah. So this is one of the point that hardware for quantum computing varies, and various industries and various researchers are focusing on various hardware aspects for quantum computation to identify which hardware can work best for quantum computing purpose. So there is a lot of research going on: superconducting qubits, ion traps, optical photons, and all these kinds of hardware which relies heavily on the principles of quantum physics. And we have something known as a quantum processing unit, QPUs. Just as we have CPUs, we have QPUs which process in parallel. So the information processing is inherently parallel. Just as we have sequential in CPU, here it is parallel. So what I consider QPU or a quantum computer is a very big, it's a very big GPU. Okay, in GPU, in graphic processing units, you have a parallel architecture. Okay, so what I called quantum computer is a specialized GPU with three properties, and these are the three properties, with the property of superposition, interference, and entanglement. So it's like a GPU, but with some special properties, and that makes it a quantum computer. So let us see these properties, and yeah, let us see. So yeah, superposition. So what is superposition? Superposition is when the qubits or more generally quantum states, they can live in a complex linear combination. Okay, how complex linear combination? Let's see. So now what happens is that, let's me start giving you. Okay, so now in superposition, what you have is that you have this state and you have a coefficient associated with that quantum state. Then you have another state and you have another coefficient, and these are normalized. So I'm skipping the normalization for now, but they are normalized. And to find the state zero, we measure a probability. We measure it through probabilities. So probability of finding state zero when it is in superposition, and alpha and beta can be complex numbers, and that's why it is called a complex linear combination. That's why superposition is complex linear combination. So what you do, you take the absolute value. And similarly for one as well. Or and also we can see that in mathematical terms now, the quantum state zero, the qubit zero, what you call qubit zero, can be represented by a column vector. Sorry, one zero. And similarly for one, you have this state. So now you can see that the qubits are represented as column vector, and this will be useful when I discuss the concept of entanglement. So what happens is that now they are in a complex linear combination, and what happens with that is that they give you the processing power, they give you the parallel processing power which I'm talking about. That's why what people say is that all the qubits are remaining 0 and 1 at the same time, but rather than saying that terminology, we use complex linear combination. That's much more accurate way of describing the superposition phenomenon. That all the qubits or all the quantum states are living in a complex linear combination, and that is what gives the quantum computer a parallel processing power where it can manipulate all the qubits at once. So that's the stuff. So if you have n qubits, then you have 2 to the power n states. And on the left, you can see the classical bits 0 and 1. So they are limited, restricted. But for quantum states, they are not limited. They can be in superposition. For the interference, what it does, it helps you to measure. It helps you to measure the superposition state. So in that, what is the phenomenon of interference is that you try to maximize a particular quantum state which you desire. You try to maximize it. So what does maximize means? Means you are trying to increase its probability amplitude. That means you want to find, for example, you want to find zero qubit. So you want to increase its probability of finding it. And that's the phenomena of quantum interference, which helps you to measure qubits when they are in a superposition state. Next is entanglement, and this is really like one of the fascinating phenomena where a pair or a group of qubits are very strongly correlated. And if there is one qubit, then its properties are heavily dependent on the other qubits. So let me explain this. How do you check for entanglement? And yeah, let's see. Right. So what happens in entanglement, and let me give you an example of an entangled state, which is like this: 0, 0 plus 1, 1. So entanglement starts happening when you have two or more than two qubits. So this is an example of two qubit case. So now we will check why did I said that this state is entangled? And the way to check is through a mathematical concept known as tensor products. Tensor products. So what we will do, we will compute tensor products. So now to compute tensor products, what we do is that we have our states 0 and 1. So we compute the tensor product as follows. So let's compute the tensor product separately for the 0, 0 state and the 1, 1 state. And this is the symbol of tensor product. And what you do here, and I will explain this. And now let's compute. So what you do, you take this element 1 and you multiply it with both the elements of this second qubit. So 1 into 1 means 1. 1 into 0, 0. Then you take this element and multiply with these two elements again, just as we did for the 1. So 0 into 1, 0. 0 into 0, 0. And that's essentially your 0, 0 state. And similarly, now for 1, 1 state, you can do the same stuff, the same kind of calculation. And this is the way in how you will identify or verify whether the state is really entangled or not. But one of the key properties of entanglement is that you cannot break an entanglement into tensor products. And mathematically to verify, that's the technique we are seeing now. So here you can do like this. So again, the same process: 0 into 0, 0, 0 into 1, 0, then 1 into 0, 0, 1 into 1, 1. Now what you do, you add them, because 0, 0 plus 1, 1. And for example, just ignore the normalization for just a moment and you just add them. Okay, so what we get here is 0, 0. And let me be very clear that 0, 0 can be written like this. And similarly for 1, 1. So 0, 0 plus 1, 1 will be 1, 0, 0, 0 plus 0, 0, 0, and 1. And now, if you see, you are getting this state 1, 0, 0, 1. And now to verify entanglement, this is very important process. Now you see, if you name these elements as W, X, Y, and Z, then you do a calculation. What is that calculation? You check whether WZ is equal to XY or not. You have to check this calculation. If it's equal, that means they are not entangled. But in this case, you see what is happening. W into Z is 1 into 1, and then you see that X into Y is 0 into 0, which is not equal, which means this state is truly entangled. So this proves that this is an entangled state, and there are other states as well, and this state has a special name. This state is known as Bell state. This state is known as Bell state. Okay, so this is really an interesting phenomena which happens in quantum mechanics, which is of entanglement, where one property, where one qubit is 0, then the other qubit is also 0. And when the one qubit is 1, then the other should also be 1. So that means that if you know one thing, you can decipher what is happening with the other thing. So if you have one system A and other system B, and if they're strongly correlated, then you know that if something is happening, if some reaction is happening in system A, then the same kind of reaction is happening in system B. So that's the like essence of quantum entanglement. And now let's return. Let's go back and see. And recently, you saw that the quantum advantage, which people were discussing, is that like when a quantum computer essentially like solves a problem, which is like a faster than classical computers. So like the quantum computer, like it's like an advantage you gain in the quantum computation world, where it is more better than the classical computation cases. And this is what Google demonstrated with their 54 qubit system quantum computer in the month of October, where they showed that they solved a problem. The problem I do not exactly remember, but they solved a problem which a classical computer cannot solve in a given time, and quantum computer was able to solve. So that's the main essence of quantum advantage. Now let us move on to quantum logic gates, because and also we will be seeing the demo as well. So you see, as you have classical logic gates, similar in the similar way you have quantum logic gates as well. And what happens is the difference between this is that the quantum logic gates need to be unitary so that they are reversible. So if you have studied linear algebra, you know what unitary means, and they need to be reversible, because that's the essence of quantum computation, that all the circuits and the number of inputs should be equal to number of outputs. Only then is that what is the information is preserved in quantum computing. In classical computing, you have two inputs and one outputs. None of your inputs goes into the output, but in quantum circuits, all your inputs goes into the outputs as well. So the number of inputs and outputs are both equal. So here I show you some basic gates, and the Hadamard gate, which is a very special gate, and this is the gate which creates superposition of qubits, which we just saw. And there is another gate, C naught gate, which creates entanglement. X gate is very similar to a NOT gate, which you have in classical circuits, classical logic gate, the NOT gate. Z gate is a phase flipping operation gate. It flips the phase when the qubit is in one state. That means in quantum state one. And these are the two qubit gates. These are single qubit gates. These are two qubit gates. Toffoli is a three qubit gate. And all these gates are represented using matrices. So that's now you can appreciate the nature of quantum computing, that you can represent all these gates using matrices, which makes you easier to perform calculations. You can do manual calculations if you just hard code these matrices, and you can then gain results which are similar to like operating these gates. So these matrices are also known as operators. So this is like an operator notation of that quantum logic gate, which if you apply to some quantum state, it transforms the state into some other quantum state. So that's the essence. And now we reach to Grover's search. So what I am going to do is that since we have seen gates, let me show you the demo for the gates and the circuit, and then we will start with Grover search. So here you can see that I have made a notebook, and I will provide you this notebook. You can play with this notebook and change stuff in this to make circuits. And now what we see here is that first we import some libraries. So let me start executing the cells. First we import the Qiskit library, which will enable you to make the quantum circuits. And we perform a X gate, which is a bit flip operation. As I told you, it's very same as classical logic NOT gate. So it's like a NOT gate operation. And if we do an X gate on 0 qubit, it will transform it into 1 qubit. And this is how visually the circuit looks like. And to visualize how the qubits are operating, we can execute this cell to know how they are. You can see the sphere, in which the sphere which I showed you in the superposition slide, that same sphere you can visualize, and you can see how the single qubit operations are taking place. So if I execute that, now you can see since X gate was applied, here you see, here is the application of X gate, and you can see that X gate being applied to 0, and yeah, by default all the qubits are in 0. So you start with the 0 state, and then you start applying gates according to your needs. So here we applied an X gate into qubit 0, into a single qubit, and then you see that the state has been transformed into 1. So the arrow shows you where the state is going. And similarly, for the Hadamard gate, which creates superposition, you can see the same result, that it will now, what it will do is that for the Hadamard case, it will not be in the Z axis. This is the Z axis, this vertical axis. And this horizontal, this is the X axis, and another horizontal, this is the Y axis. So in X axis, the Hadamard reaches the X-axis. This axis is also known as the diagonal axis. Y-axis is also known as the circular axis, or the clockwise counterclockwise axis. And yeah, let's see, visualize. So you can see this is essentially the state 0 plus 1 divided by root 2. So if you apply Hadamard, so okay, so if you apply Hadamard to 0, then you will get that state. which is 0, which I showed you in the superposition slide, that same state divided by root 2. And if you apply Hadamard to 1, then you will get this state. Now, the important thing to note here is that, and you can try this yourself, of course, later. And yeah, this state is known as plus state. This is also known as the plus minus basis, the plus state, and this is known as the minus. So the x-axis which you saw in the sphere, the x-axis, this is also known as diagonal or plus minus basis. So what happens is now is that since I told you reversible, and now you can verify this yourself later, that if you apply Hadamard to plus, you will actually return back to 0. And if you apply a Hadamard to minus, then you will return back to 1. And that's the power of reversible computation which happens in quantum computing, and that needs to happen. So you can implement circuit in any way around, and all these operations make sense. That's because of the unitary nature of the gates, and all the matrices which we saw for the quantum logic gates just now, they are all unitary in nature, which preserves information. So now let us see, and yeah, before yeah, so let's see. So let's see the phase flip operation. So this is the Z gate. So what we did is that first we applied a Hadamard, and then we applied a Z gate. So here you can see, here we have applied the Hadamard, and here we applied the Z gate onto the qubit. And you always start with a quantum register, you make a quantum circuit, and then you start applying. These are all single qubit operations. And here also you can visualize the state. So now what will happen, since you have applied H into the 0 qubit, that means you are in this state, you are in this state. Now if you apply Z, so the operation of Z is given like this. So if you apply Z, what Z does is that if you have 0 qubit, it won't do anything to 0 qubit. But if the qubit is 1, it will introduce a negative phase for that 1 qubit. And the same thing happens here, and you can see this very clearly when you visualize the circuit, that as soon as I execute this, and you can see that this arrow is now on the other side of the x-axis, which means 0, which means qubit 0 minus qubit 1 divided by root 2. That means it's in this state. It's in the minus state. Earlier, it was in the plus state. This is the plus state. Opposite of that, it's the minus state. So that's essentially the operation of the Z gate, because if you start applying Z gate to this, then first you will apply Z to 0, nothing will happen. Then the Z will go here because of linearity. You will apply, that will turn into minus 1. So ultimately you get the state minus. And that's the essence. Let's move to 2 qubit gates. CX gate is commonly used to create entanglement. And I didn't show you the
Sir, a little bit of
yeah,
zoom to the of the notepad so that they can really get to know each and every line.
yeah, yeah. All right. Okay.
No, actually, control and the scroll. Yeah,
Yeah,
that's it.
yeah, I have done control and scroll. Is it visible now?
A little more, sir, because if it fills the entire screen, it would be better. Yeah, this is better, sir. This is better.
All right. All right. Good. So now, what happens now? Let us see the CX gate in graphics. So this is how a CX gate looks like. And what is the operation of CX gate? Let me define it. The operation of CX gate is something like this, that whenever you have two qubits, so CX is like this, so CX gate. So for CX gate, if you have qubit, if the first qubit, so let me draw it here also so that you can appreciate this in a better manner. If you have these qubits and if you initialize it with 0 0, for example, if this is the first qubit, okay, so let's suppose that this is the first qubit. All right. All right, what's happening? Yeah, qubit 0 and this one is qubit 1. So let's see, qubit 0 and qubit 1. So if you have them like 0 0, and then at the output, if you see the output, because since now you see the inputs are also being fed in the output as well. So what you will get at the output, and this will define the CX operation. When the first qubit is 0, nothing happens to the second qubit, so you remain as 0 0. So all the states transferred as it is. Again, if the first qubit is 0, second qubit 1, same thing, because since the first qubit is control, so this is known as control. This qubit is known as the control, and this qubit is known as target. So it's a controlled target, controlled not gate, X gate, controlled X gate. That is what it is called. This is the target. Okay, now same thing. And now if you apply 1 in the first qubit, but your second qubit was in 0 state, it will flip the order. It will flip the second qubit. So now the first qubit as it is, and the second qubit will be flipped. And then you have the 1 1 state. So first qubit 1, second qubit also in 1 state, but it will turn into 0 state because it's a CX gate, as we learned, control and target, and the order matters in this. Okay, so this is the operation of CX gate, and very similar to that, operation of CZ gate, which is a control Z gate, that also happens when your state, that also happens when your control is in 1 So for the zero, when you apply Z gate, it won't do anything. So for the CZ gate, what happens? For the CZ gate, this line changes. This line changes as follows. So whenever the control is 1, target is 1. Target is 1 means now your output should be Z of 1 is -1. So that means the first qubit will be 1 and the second qubit will be -1. So this is the Z gate, CZ gate. Rest of the stuff remains the same. So you get the idea, I hope. What is the meaning of a control and target gates in quantum circuits? Because I don't know why this pen is creating so much problem. So yeah, let's go further. And yeah, so that's the CZ gate, and you can show CZ gate like this, or you can show CZ gate like this also. In many in various notations, you will find that either you show like this, so something like this, and for QuizGit you show it with like this in the QuizGit. So that's the circuit for CZ gate. All right. All right. So now let's see what happens. So now this is like you can create CZ gate utilizing the CX gate and H gate. So these are various ways of creating the same circuit, and the same thing can be done with the CX gate as well. You can create the CX gate utilizing the control Z gate and the Hadamard gate, and the circuit will look as follows. So these are some of the different ways of creating all those controlled gates with the help of other gates. It's like a combination of single qubit and multi-qubit gates. Now we come to Toffoli gate. So for Toffoli gate, what we have is this gate looks like follows. So here now we have two controlled bits. So Q0, Q1, Q2. There are the qubits are the two of them are controlled, and the third one is the target. So that means again the same operation will apply. When both of them become one, then only this bit, the third bit, will be flipped. So it's like something like this. So for CCX, all right, so let me see. So for CCX, when will the changes happen is that if your Q0, if you have Q1, and if you have Q2, and then you have the outputs. So this is now a three qubit gate, and now so the changes will happen only when both of the qubits are one. So if, for example, this qubit is also one, this qubit is one, rest of the cases remain same. Then only if the state was zero, then you will achieve one, one, one. And similarly, if this is one, if this is one, and now if you have this state as one, then you will get one, one, and zero as the output. So the third qubit, Q2, the third qubit is being flipped. Why? because these two are the control, and the controlled ones happen when that control qubit is in one state. So very there's the same concept as the CX gate only. Very same. Only thing is that the multiple two qubits are now controlled. In the CX gate is but only single qubit being controlled. So the target qubit flips when the control is in one state. That's the essence. Now we see some classical logic gates being implemented using quantum circuits, and the advantage of this is that since classical logic gates are not reversible, but the quantum gates are reversible. And for that, you might be already familiar with the like a truth table of classical logic gates, and now it will be a good exercise for you to revise those truth table and compare it with the classical the quantum circuits which I am now showing you, and just try to verify how those truth tables will be uh, uh, will be working according to the circuits which I am going to show you. So that will be a good exercise for you to go through. So let's see NOT gate. So this is the NOT gate. So this black sign is the measurement operator. After you apply the quantum gates or after your quantum circuit, you can measure the qubits, and this operation is a classical operation. That means after applying measurement, you can never go back to achieving that previous state which was present inside the quantum circuit. Why? Because the superposition collapses. The superposition collapses, and you go into one of the basis states. So you collapse into one of the basis state which gives you the measurement. And also it is noteworthy to mention here that if you measure, if you have a superposition of 0 plus 1 divided by root 2, and if you measure 0, if you measure it for the first time, and if you collapse into the state 0, and if you measure it immediately again, then you will keep on attaining the state 0 with with some probability. If you consider the generic state, then you will have the absolute value square alpha squared, which I discussed before. That probability of that particular state you will keep on achieving after every repeated measurement. So yeah, that's one of the important stuff to note. So this is the NOT gate, and NOT gate, as I told you, it's the just the bit flip operation. So the circuit is very simple. And AND gate is a CCX gate. How that is a CCX gate, now I want you to verify this later. After this lecture, you just go through, compare the truth table of AND gate and the CCX gate operation, and just see that how similar they are. So that's the AND gate. And I want you to verify this. This is your homework. You should verify that why CCX gate is a AND gate for the classical case. What about NAND gate? Just a NOT operation will be there, isn't it? So CCX plus a NOT. NOT means X gate. And that's the case. The case of OR gate is a tricky one, and I won't show you here. It will take some time, but yeah, I think you will be able to verify this again. That's also the same logic with which you can verify the AND gate, and you will see that it really makes sense when you start verifying this. Because remember, here you have to take the output into account as well. So yeah, so whenever you are comparing it with the truth table of your classical circuits, consider those outputs as quantum registers as well. So like each line here is meaning a quantum register. So while making the comparison, you can compare it like that, which will make your comparison a bit easier. So this is composed of CX and CCX gates. And XOR gate, what is XOR gate? XOR gate is CX gate itself. Because as we see, the XOR operation is, if you see the CX gate carefully, then if you see this line, if you see this column is nothing but the output, this column is nothing but the output of XOR gate. This column is nothing but the output of a XOR gate. So now you need to again verify how the CX gate is an XOR gate. Again, just compare the truth tables of the CX gate, which I gave you, and with the classical XOR gate, and you will see that it matches. And yes, half adder circuits, since you all are from engineering background, most of you, so you will recognize that a half adder circuit is composed of a XOR gate and a AND gate. And since you have learned both of them above, so you can make the circuit very easily, and the circuit will look like this. So you can see here is the XOR gate, just as I showed you, this one, plus AND gate, which I showed you here, which is the CCX gate. Very simple. You just apply them and you just measure these output qubits. These are the output qubits. So this is just like a IBM quiz kit demo, which I will be providing this notebook. Don't worry. You can try to make full adder circuit as well for this. That also won't be very difficult task, and yeah, you can make it with the help of CX and CX and all those gates, a combination of those. And yeah, just have fun with this notebook. I will definitely share with everyone. So let's move to uh, because yeah, time is running out.
Sir,
And
and also,
yeah.
sir, and
Hmm.
also, please give the
Hmm.
Google Collab link so that I can put it in the YouTube video thing, so that it will be much
Okay,
more
I
useful
am not
after
doing
hearing.
it in Google Colab. I would recommend everyone to just have their environment set up. It's just a
Yeah,
simple pip
but
install
environment
Qiskit.
setup was taking too much time because Conda is not being installed.
Okay, I
No,
think
Conda
some
is not.
people might be facing problems with that. I will make a collab notebook and send you the link.
Sure, sir. Sure, sir.
Yeah,
Thank you
yeah.
so
I
much.
will make that and definitely send you.
Yes, sir. Thank you.
Okay, thank you. Thank you so much. And okay, so yeah, so let's now proceed towards the Gruber search. Uh, yeah, so let's have a look at the Gruber search. All right, so let's see what is Gruber search algorithm. Gruber search. So, in the case of classical case, as you know, in classical computing case, you take the search algorithms. When you take the search algorithms, linear search, for example, in classical case, let me write it here. If you take the case of linear search, okay, linear S, I'm just writing in short. Okay, so linear S, you will find that its complexity is given by O of n. And what essentially it means is that if it's the worst case scenario is that if you are searching through a database or an array for a particular element, and if that element is located at the nth position, that means nth position is like you can see it as like an end of the array or the end of the database, then it will take n searches to search that element. Similarly, another algorithm, which is the binary search, which is better than this one, linear. Okay, that has somewhat better complexity, which you can say it as log of n. So it takes less time than O of n, but for binary as well, you need to get your database in a sorted manner. So in this case, you have the sorted stuff. You need to do the sorting. So database or array should be sorted. But in Grover search, the beauty of Grover search, and that's why this is very interesting, is that this is an unordered search. What is this? This is a un this is a unordered search. Okay, that means your database can be unstructured. Your database can be unstructured. Your database, and this is very important to note, because for the binary search it is sorted and it is structured. Sorted means structured, but in the Grover search it is unstructured. So this is also known as an unstructured search. So in that, if you are getting a speed up for the classical case, it will take a long time. If your database is unstructured, it will really take a long time to do linear search or the binary search if it's unstructured. But in the Groover search, what we see is that we get some potential speed up. We get a potential quadratic speed up. What we get? We get a quadratic we get a quadratic speed up in the Grover's case. And for that, we have the complexity as O of root n. All right. So this is a quadratic speed up, and this is very significant because your database or the array is unstructured, but still you are able to get a quadratic convergence. And that really matters a lot, because, and why this happens is again the same phenomena. Quantum computing employs the power of superposition. That means it's inherently parallel. It is able to process all the information in a parallel manner. And that's the advantage you get. So now, and of course, entanglement is also there. So all those gates which you studied, all those gates are being used to take advantage. For example, Hadamard is used to take advantage of the superposition. C naught is being used to take advantage of the entanglements. So that's the thing. So let's get started with Grover search. So what happens in Grover search, and I will show you graphically to illustrate the things in a better manner. I try to reduce the math, of course, so that you don't feel boring with the math. So if you have some number of items, okay, for example, if this is, so if you have like this, in all the items you have this, and then you have a different item. For example, let me show it with a different color. You have this blue item, and then you have all the other items. So this blue item is your state W, or you can call it X star or anything. So this is your state W, which is the state, which is the marked state. This is the marked item which you are searching for in an unstructured database. This is your unstructured database. Each is having an amplitude, each is having, and here is the amplitude, and this is important to note, each is having an amplitude of 1 by root n. Okay, each is having an amplitude of 1 by root n, and you want to search for this element. So what you do in a simple case, what you do, what Grover's oracle does. So Grover's algorithm consists of two steps. What are those? Grover's algorithm. Okay, so Grover's is consisting of two steps. One is the oracle. You make the oracle plus something known as diffusion. Something known as the diffusion operation. Now, what happens if you make the oracle as a phase oracle. That means it flips the phase of the marked items. That means the W item. So what we will do, if we apply the oracle, if you apply the oracle, for example, you apply the oracle U of F, and now what it will do, its operation is to flip the marked item. So now you do the same diagram again. Okay, and this is the same line. Okay, but now it will be a little bit reduced. Okay, so what this line will become, and I will show you that these are getting reduced. So now you will see when the flipping operation happens, it is now reduced. And now let me draw it with the same color. Now your phase is here, and these are the other phases. These are the other marked items. Okay, so you have this here as, this is the same as 1 by root 10. Here you reach minus 1 by root 10. And now what happens is that you apply this diffusion operation. So oracle is the UF which we applied just now, which flips the phase of the marked item. And now you apply, this is the operation which makes Grover's wonderful and helps you to search. And this is what, like, which I told you, the phenomenon of interference, where you maximize the probability of a certain state so that you can find it easily. That's the, like, taking advantage of the quantum interference phenomena. So let's denote this as U of psi. So if you apply U of psi to this, and you will see that this is being amplified twice, then the other ones will become more shorter. So now it happens like this. So others become more shorter, and now your element which you want to find is having the maximum amplitude so that you can find it very easily. And that's what Grover's algorithm is trying to do. It helps employ the phenomena of quantum interference to help you find your marked item. So let me be specific that this is the marked element. So this phenomena, this is basically the phenomena of Grover's search. That first it flips, and after flipping, then it amplifies double times. So by, and flip with a flip plus amplification. So that's the main operation which is happening in the diffusion operation. And this operation, mathematically, this operation is known as, you can read about this more later, inversion. This is known as inversion about the mean. Okay, this phenomena, this is mathematically, this is known as inversion about the mean. Okay, so this is essentially the Grover search. So now you can see how cleverly a mathematical phenomena can be used to amplify the state, and then with the help of this, and also, like, with the help of this quantum interference phenomena, since now you have amplified that state, that means the probability of finding the marked state is higher. And it turns out that to find, if your database is very large, and this is also very important to note, if your database is very large, or if your array is very large, then this whole operation is repeated root n times. And that's the complexity which I mentioned here. And that's why Grover's algorithm provides a quadratic speed. And now you might ask that why root n times, and that's one of the reason that the reason behind that is that the square root of the squared amplitudes is in the square like the probability of finding a state, like the square root of probability is actually the amplitude, the absolute value of the amplitude, and because of that only you have the root n there. So that's the essential, that's the main concept of Grover search. Let us now move on to the uh, implementation of Grover search. So so here I have ready. All right. So again we start with importing all our Qiskit libraries. And first of all, this is the first step of Grover's oracle as we studied. We make the phase oracle, which will flip the phase of the marked item, and it is shown like this. You have already seen this. This is the CZ gate, the control Z gate. And now you make this diffusion operators, which consist of first applying the Hadamard gate so that you make the superposition of the qubits, and then you apply the H and CX and H gate, which is also the control Z operation. All these circuits you have already seen. We have combined it together to make the inversion about the mean operation happen, and which is essentially the Grover's diffusion operator. So now in this circuit, you see we start with the superposition, we apply our oracle, and then this whole circuit is your Grover diffusion operation. So that means this whole circuit is doing this job of making the amplitude large and then flipping it back and making it highly probable to find for us the marked item. That's the operation of this circuit, and that's why this is really important. And after that, you take measurements, and here we were marking the 1 1 state. As you see, as I mentioned here, the circuit marks the 1 1 state. That means you know your solution, you know your marked element, you just marked it already, and then you just uh, applied the Grover algorithm to find it. So if you see the answer, if you run this using a quantum simulator known as quantum simulator, if you run that, and then you will see that with 100% probabilities, because as I told you many times the experiment is run, you can see 1024 times it's run shots. After it runs for 1024 times, you will see that there is a high probability, and this, since this is a simulator, that's why it's showing perfect result. If you run it on a real quantum hardware, you will receive less than 100, because as I told you, quantum hardware is not perfect currently, and there is a lot of research happening in that area to make our qubits perfect, because none of the qubits which currently we have present is not perfect. So IBM, for example, uses the superconducting qubits, superconducting hardware to make their qubits, and that's also not perfect, because the qubits are very fragile. It doesn't need to it first of all it has to be isolated. It should not interact with the environment. As soon as it interacts with the environment, its nature, its quantum mechanical properties are lost. So we don't want that to happen, and that's why it is really difficult to have a qubit which is very perfect like a classical bit. So on a simulator, you will get these results, but if you run it on a real quantum hardware, that will be, in that case, you will receive results which will be the highest, but you will receive the other probabilities as well. That means 0 0 0 1 1 all those states will also come with some probability, but you will see that the Grover's algorithm has worked and it has amplified that marked item state, and you have a higher chance of finding that state. So that's really the essence of Grover's search algorithm. And now we are complete with this. I have showed you the demo, and yeah, now it's time for some Q&A. Let me take some doubts you might have got between the session.
Yeah, guys, you guys can actually give out your Q&As. You can just ask the questions in the chat box so that it will be easier for us to answer. Or else you can just give me a request to unmute. I will unmute. You can ask the questions. So yeah, that's how it is. Anybody, any
I can
doubts?
see Anuj has answered quite a lot of questions. Thank you so much,
Yeah,
Anuj, for helping me out there. You have answered a lot of questions and like you have
I think Anuj
reduced.
sir, I think
Yeah,
probably I'll unmute you so you can just give your
yeah,
thoughts about this.
definitely because
Yeah.
Anuj is also there on the group which I am leading for quantum machine learning. So
Okay, okay.
I think he's.
I've asked him to unmute, so yeah.
Yeah, hi, this is
Yeah, you can
Anuj.
turn on your video also, sir.
Okay, give me a minute. I'll do that.
Yeah, I think thank you, Anuj sir, for giving such an wonderful insights in the and the
Yeah,
clarification for
thank
the
you. Thank you
yeah.
so much, Anuj sir. That was really wonderful. You are muted. Your microphone is not on.
Yeah,
Yeah,
am I audible
Yeah.
now?
yeah,
Yeah.
yeah.
You are audible. Yeah. Yeah.
Okay, okay. Yeah, so I was just trying to answer few, I think,
Yeah,
because you were,
thank you, sir. Really, it really means a lot to me because otherwise I have to take a lot of questions and yeah, I'm speaking
I
continuously.
thought like something if I can answer, I think that will help so you can proceed at your
Definitely.
pace.
No, that's I'm really grateful. It helped me a
Yeah,
lot
actually,
and
Anush sir had actually given. Actually, I also had a little bit of doubt because I have my exams and I could not give too much time because I'm an EC student. I
No,
can't give time for quantum now.
not an issue. So just I think one point because this is something which actually started with because it is quite I think a point which creates a lot of confusion was
mm,
around the supremacy, and the reason why I was actually trying to clarify, because same point
mm,
is actually, though everybody actually tries to confuse it with how IBM challenged it to Google, but thing is supremacy itself will only come into scene once we are actually having a quantum computer which can do each and every task, okay, with a better performance, okay, and
mm.
a better
Yeah,
capacity.
John Preskill actually named it, but was never being achieved by any computer till today. John Preskill actually did that, but nobody actually.
Qubits should be
Yeah.
perfect. They are entirely not
Yeah,
perfect currently. So that's like a lot
Yeah.
of research is
So, so,
being
so
done. Mm,
advantage, what we are achieving as of date, even the Chinese one, which actually happened in actually an experiment. So
mm,
that also is actually only fine tuned for a single task only. Okay,
mm,
yeah,
so we yet to actually see a quantum computer, which is actually in real sense universal computer. Okay, so that universal computer, once we achieve that particular level, then it will be quantum supremacy.
mm.
But as of date, and that's why rightfully D wave uses only quantum advantage. Okay, they
Quantum
don't say
advantage.
it.
Yeah, exactly. Mm. No, not
Okay, so D
supremacy.
wave,
Mm,
yeah, supremacy is not being used. It is only like even like the Chinese actually also use because of the reason of why Google used it. Okay, so they
mm,
are saying that if it is a supremacy, then we have achieved a better performance than even like what Google did. So it was, and just I think you might have actually also heard of. I think there were a few sessions from Keyword around this particular
mm.
boson sampling.
Yeah,
Okay,
boson sampling. Mm,
that was a experiment which was conducted by Chinese. Okay, so it was a very specific experiment which was carried out. So it was not the all the operations which we can perform. Okay, because there are many use cases like it is
exactly.
in finance and everything. So not every, because machine learning, there are many algorithms which are still performs, I think, and Srijoy can actually comment better than me, but there are many such algorithms which performs better on like
Classical
classical
computers.
computers
Yeah, exactly.
than even on this quantum computers.
Currently we have not reached that stage actually where quantum machine learning can really show some magical effects. Just as like
Yes.
we say that, yeah, like what we do all is that everything is in theory, but putting into practice is really difficult. So that's the that's the thing. Like, so classical machine learning for now is much more better than quantum machine learning, I should say.
Yes. Yes.
In theory it definitely looks good. So when we have perfect quantum computers, then quantum machine learning will be, yeah, it will be much more nicer.
Yeah. So it is a NISQ era which we are
Yeah,
in.
NISC era,
Okay.
yeah.
So yeah, so it is a NISQ era which we are actually as of now in, and NISQ era, like, and that's why how we classify. And just sorry, I will take only few seconds only.
No,
So
not a
there
problem.
are three categorize. Yeah, there are three categorization. And just want to add the explanation from Sujoy
Hmm.
that there are three category of quantum computers also. Okay, so we have should actually also know what, because we normally do the classification of the classical computers, but there are three type of actually quantum computers also. So one is analog computer and analog quantum computers, which actually covers the quantum annealing. So they are not actually the real quantum computers. The annealing is not a real. It is actually a form
Hmm.
of adiabatic computing. Even the
Adiabatic, yeah.
real, yeah, adiabatic computing is also not realized. So quantum annealers which D-Wave used, they are not said to be the real quantum computers. So they come
Hmm.
under the category of analog quantum computers. Then the type of actually universal circuits which we are actually using, okay, the Shor's algorithm or
The
Grover's
gate oriented.
algorithms.
Hmm.
Yeah, so they are gate oriented, and the third category is which we are, I think we are trying to explore the NISQ era. So that is this particular variational
Yeah.
like quantum algorithms which we have.
Hmm.
The
Exactly.
VQE or VQLS. So these are the, and the most of the work, and which is actually where machine learning is also leveraging. So we are using machine learning to train the this quantum circuits. So that is actually a form of VQE. Okay, the variation quantum
Quantum algorithm.
eigensolvers type of algorithms. It is that thing which is being explored by many areas. It is not limited to only machine learning, optimization is there, chemistry, everything is they're using the variational form of that.
Hmm.
Okay, so just I think just
Yeah,
wanted
that's,
to add.
thank you so much, sir, for adding that information. Actually, that's truly very nice, and I'm really thankful to you. And yeah, I hope that
Sure.
everyone appreciates this fact. And yeah,
Yeah.
so that's the thing. So thank you so much.
Okay. Yeah. Thank you.
Yeah, I think I don't have anything to say, and it was a wonderful session. Thank you,
Yeah,
Srinjoy,
thank you,
Ganguly
Vishwas,
sir,
for
for,
inviting me.
yeah. And also, folks, if you want to join the Computer Architecture Club and the Pi and AI community, which is under me, you can just contact me through the LinkedIn. And contacting me through the LinkedIn, probably it is going to help you in gathering more information for the deep learning hardware and also such workshops which we will be conducting in the future. So yeah, you can join to me in the community and connect me through the LinkedIn. And I also will give my mail here, so anybody wants it, so they can mail me here. Vishwas 9234